All right, here we go. 7.6. Now we're going to take what we know about exponential and logarithmic functions and we're going to piece it together. We're going to start off with the definition. Exponential equations are equations in which variable expressions occur as exponents. So we have what's called the property of equality for exponential equations. If you have b to the x equals b to the y, that's true if and only if the exponents are equal. So for example, if I have 3 to the x equals 3 to the 5th, that's true if the exponents are equal. X equals 5, okay? I want to point out I am not canceling the bases. I'll hear students say, okay, you cancel the 3's. I'm like, no, we're not canceling the bases. We're saying the exponents are equal, okay? In example 1, I have 4 to the x equals 1/2 to the x minus 3 power. So right now they don't have the same base, but I can get creative here and I know 4 is 2 squared and I know 1/2 is 2 to the negative 1. Then what I'm going to use is I'm going to use this exponent property that says a to the m to the n power is a to the m times n. So now I multiply the exponents. Now I have the same base, so I'm going to set their exponents equal to each other. Adding x, I get 3x equals 3, so x is 1. All right, try example 2 on your own. I'm going to give you a head start on me. You guys don't skip steps, okay? There's no rush to doing these. And if you skip steps, you're going to get yourself into trouble. So I'm going to rewrite 9 as 3 squared, so that's 3 to the 4x. I'm going to rewrite 27 as 3 cubed. Now be careful on this one, because you take 3 times the x minus 1, so that's 3x minus 3. Now the exponents are equal, so x is negative 3. Okay, any questions on that one? Okay. All right, when it's not convenient to write each side of an exponential equation using the same base, you can solve the equation by either taking a logarithm of each side, or you can go from exponential to logarithmic, okay? And remember when we did 7.4, I said to you, it's really, really important that you remember that, going from exponential to logarithmic, logarithmic to exponential. So this is going to be log 11 base 4 equals x, okay? If you have the TI-83s, let me go over this again, how you do it with change of base. It's just ln 11 divided by ln 4. If you have the TI-84s, you can do alpha window and it'll do it for you, okay? So x was about what, 1.79? All right, try example 4 now on your own. Rewrite it in logarithmic form and then use your calculator. sorry, this one was 1.73, right? Okay, sorry about that. All right, in example 4, I got 1.62. If you're sitting there thinking, how is she doing that, and you have forgotten 7.4, come in at lunch, math study table, and I can, reteach it, go over it again. All right, Newton's law of cooling. This is actually some calculus concepts that we are going to lay the foundation for. It says, Newton's law of cooling. This law states that for a cooling substance with initial temperature T sub 0, the temperature capital T after T minutes can be modeled by this formula, where T sub R is the surrounding temperature and R is the substance cooling rate. There's actually a similar formula to this that I don't mean to get so gruesome, but you know how like when they discover a dead body, they can actually take the temperature of the body, the temperature of the surrounding area, and some other factors, and then tell you, and that's how they determine the time of death. Cool. I like that kind of stuff. I like to see science, in action. So in example 5, it says you are driving on a hot day when your car overheats and stops running. It overheats at 280 degrees Fahrenheit and can be driven again at 230 degrees Fahrenheit. If R is 0.0048 and it is 80 degrees outside, how long in minutes do you have to wait until you can continue driving? This would be a problem you might want to know. So let's start with our formula, just copying it down. Remember, T sub 0 is the initial temperature. T sub R is the temperature of the surrounding area. Capital T is like your ending temperature. R is the rate, the cooling rate as a decimal, and little t is the time in minutes. So let's go back through the problem and see if we can identify what each of our numbers are. It says it overheats at 280 degrees Fahrenheit. What letter does that one represent? Good job. Yeah, that's T sub 0. That's our starting temperature, right? The car is currently at T sub 0, 280 degrees Fahrenheit. It can be driven again at 230 degrees Fahrenheit. What's that? No, that's not our surrounding. Surrounding temperature is like, what's the temperature of the room? What's the temperature outside? So no, 230 degrees is not T sub R. It's T. It's not the exponent. Little t is time. Okay? This is the temperature we needed to get to before we can drive it again, right? There's our R. Now, what's 80 degrees Fahrenheit represent? That's T sub R. That's the surrounding temperature. And we're trying to find little t. T is the time in minutes. So let's plug everything in. Now I have 230 equals 280 minus 80 times e to the negative 0.0048 t power plus 80. So being able to solve exponential equations opens up a whole new world for us in terms of what kinds of problems we can figure out. Thank you. All right, so here we go. We're going to start by, we're trying to get the e term alone. So we're going to multitask here. We're going to subtract 80 from both sides. And I'm going to get 150 equals 200 e to the negative 0.0048 t power. And then I'm going to divide both sides by 200. And I'm going to get 0.75 equals e to the negative 0.0048 t power. Now, I want you to notice this is actually the same type of problem as example 3 and 4. My basis can't be the same, so it's not like example 1 and 2. So I'm going to go from exponential to logarithmic. The base is e, so that tells me log base e is ln. So it's going to be ln 0.75. The answer to the log is the exponent. So I have ln 0.75, which is some decimal. And then I'm going to need to divide by negative 0.0048. When I did that, I got 59.93, which is really about 60 minutes or 1 hour. So if you wanted to write your answer as a sentence, we would want to say it takes about an hour before I can continue to drive. Okay? Something along those lines. This is awful. Okay. All right, now we have logarithmic equations. Logarithmic equations are equations that involve logarithms of variable expressions. You can use the following property to solve some types of logarithmic equations. We have the property of equality for logarithmic equations that says if log x base b equals log y base b, that's true if and only if their insides are equal. So for example, if I have the log of x base 2 equals the log of 7 base 2, then the insides are equal. Now, we have a note here. You must check domain in logarithmic equations, because if you remember from our definition of a log, you can't have negative numbers inside a log, and you cannot have 0 inside a log. So let's start with some examples. In 6, letter A, I have a log on both sides, so their insides are equal. So I get 4x minus 7 equals x plus 5. I can subtract x and add 7, so x is 4. Now what I mean by check domain, you're going to take your answer and plug it inside each log to make sure it's positive. So 4 times 4 is 16. 16 minus 7 is a positive answer. 4 plus 5 is a positive answer. So it works. So now you guys check letter B and check your domain. Okay, I have 2x plus 8 equals 6x minus 12. If I subtract 2x from both sides and add 20, I get x equals 5, and I check it in both, and it's okay. All right, no problems. All right, now, what if you don't have a log on both sides? What you can do is you can just rewrite it in exponential form. So in example 7, letter A, this is 4 to the 3rd power equals 5x minus 1. So if there's not one log on each side and that's it, then I've got to try something else. So you use your rewriting into exponential form. So now you can begin to see why that was so important.